It's not sure, not at this point. So আমি তোমাদের একটা কিছু বলে দিলাম, সেটা পরে দেখা গেল যে সেটা মিটিংয়ে সেরকম কিছু হলো না। That would be creating some problems, right? So just wait for it. আরো দিন ওয়েট করতে হয়েছে, আরো কিছুদিন ওয়েট করতে হবে। তবে এটা মোটামুটি বলা যায় যে জানুয়ারি মাস থেকে তোমাদের নেক্সট সেমিস্টার থেকে প্রবলি it will be normal. Means, physically all the classes would be happening and all the labs will also be happening. But then again, it's open to interpretation. পরে সিচুয়েশন কি চেঞ্জ হয় তার উপরও ডিপেন্ড করবে, এখনই কিছু বলা সম্ভব না। So we'll confirm that date maybe in next week's class. Date both the date of the class test, and for this class test the syllabus would be the introduction part and the non-linear equation solution. Okay, that would be the extent of the syllabus. Yes, that is part of introduction. That means there was an introductory class, there was a class on errors associated with numerical analysis, and then there was number representation. After that, nonlinear equations. So these four will be there. Later on, there would be another test at the end of the session. Your academic session is getting over by 18th of December. So around that time, 18th, 19th, 20th December, that time I will take another test for numerical analysis, and that would contain the whole syllabus. Okay, so this one is probably less than even half of the syllabus. The final test would be comprising of the total syllabus. So in a sense, probably easier to score in this one. To prepare well for this, go through the video lectures as well as any kind of material that have been provided, and questions will not be that difficult. Is that understood?
কোশ্চেন গুলো কিরকম টাইপের হবে, মানে প্রোগ্রামিং, মানে আমি টাইপটা জানতে চাইছি জাস্ট।
Programming will not be there in this one. Programming will be there in the final test. Okay,
মানে পেন পেপার টেস্ট হবে না কিরকম হবে স্যার?
Maybe there would be some objective type questions,
Google form based,
but there will be some questions which you will need to answer on paper also. Write it on paper, take a snapshot, upload the photo or scan. Is that clear?
Yes sir.
Okay. So let's now start the lecture. I will have to start. Should I record or?
Yes sir.
Okay. So hello and welcome to another numerical analysis lecture, and the topic of today's lecture is numerical integration. Here we are going to look at two different methods of performing numerical integration, namely the trapezoidal rule and the Simpson's rule. More specifically, we'll be looking at Simpson's 130. So let us begin. We are familiar with the concept of integration from our basic understanding of calculus, which we have come across in our higher secondary studies or even in engineering mathematics in your previous semesters. We also know that there are two types of integrations. One is the indefinite integrals, where we obtain the result as an expression with a constant, and there is also the definite integrals, where we at the end of it get a solution in the form of a number. As we are in the domain of numerical analysis, which exclusively deals with numbers, we are at the moment interested in the definite integrals only. Now, integral of a real valued function, let's say fx, with respect to a real variable x on a given interval ab is given as follows. We are all familiar with it. We are also familiar with the physical interpretation of a definite integral. What is it? If we have this arbitrary function, general real valued function of fx, then its definite integral within the given domain a and b is basically the area under the curve. So here we have the definite integral. Just a moment. So in this expression, fx is the integrand. Fx is known as the integrand, whereas dx is the infinitesimal strip on the basis of which the integration is performed. And as a result, this is also the variable on which, or with respect to which, the integration is performed. We also know that what is a and b, these are the limits of the definite integral, definite integration. A is the lower limit, b is the upper. As I said, physical interpretation of this definite integral is that it represents an area, assigned area of the region in the plane that is bounded by the graph of the given function fx between the two limits on the real axis, a and b. So this is the integral. This is what we are solving for. So that gives us an idea what is the objective of the numerical integration. The objective is to find out the area under this curve in an approximate way. Of course, we have the analytical methods. You have already gone through those analytical methods where you solve integrations by hand. But here we are not looking at those exact methods. What we are looking at is some approximate way of finding out the area under the curve, which actually represents the definite integral. But why do we want to get such a approximate method when we have the analytical methods? The reason is that some of the functions cannot be integrated analytically. There are certain functions which are difficult to integrate, obviously, and it involves quite a lot of mathematical manipulations, calculations. So even if the closed form integration formula exists, that means you can obtain it through analytical methods, it is not easy to do so. So applying numerical integration has to do with ease of obtaining the solution. It might be the most efficient way of calculating the integral. And finally, a function may not be given as a closed form expression. The function fx that we have talked about, this function, this may not be given as an expression. It may be given as a tabular data. Some discrete data points, xi's and yi's, may be provided as information of the function. We have seen these kind of functions in our previous two classes where we have done regression as well as interpolation. So if it is given like that, then numerical integration is the way to go. That is where you apply numerical integration. So these 3 points are important to remember. When do you apply numerical integration? When a function cannot be integrated analytically, when a function is difficult to integrate and the mathematics involved becomes too complicated, then you can apply numerical integration. And finally, when discrete data points are provided as a function, the information of the function is given in terms of those discrete data points, then you will be going for numerical integration. So from here, from the basically the last point, we can identify two broad categories of numerical integration. One is where the function is known as a closed form expression, so numerical integration of a known function. In this case, this is just a repetition of what we had seen in the previous slide. You have the function fx, you have the limits a and b, and you try to find out what is the value of the definite integral. That means the area under the curve bounded between the two limits. The next one is numerical integration of a tabulated function. It means that the function is not given as a continuous curve. Only the discrete data points as shown here in the xy plane is provided. So what can we do here? We can perform an interpolation in between the points or the limits a and b. The discrete points are given. We can fit an interpolating polynomial of the nth order f and x through these discrete data points. And once you have fitted such a polynomial, which may be of the form a0 plus ax plus a2x square going up to an x to the power n, then it becomes quite similar to what we had done in the first scenario. Now your task is to find out the area under the interpolating polynomial. Here we have, let's say, n plus 1 data points. If there are n plus 1 data points, then we can fit a polynomial of nth order through those data points. So it is just another way of saying that we'll be first of all looking to perform an interpolation so that the interpolating polynomial can be found out. And here what your task is to find out what is a0, a1, a2 going up to an. So basically finding out the coefficients. How can we do that? We have n plus 1 data points. So from those n plus 1 data points, we can write down n plus 1 equations in n plus 1 unknowns. These unknowns are obviously a0, a1 going up to an. So n plus 1 unknowns with n plus 1 equations. We can solve for these unknowns. Once these unknowns are known, the polynomial is completely known, and then you can apply the same methodology as we did in the first scenario here for the closed form function. Only in this case, you will be integrating the nth order interpolating polynomial. So basically, these two are considered as equal. Now here I would just like to mention that what is the simplest polynomial that we can fit through these points? We can go for a linear polynomial. Then we require only 2 points for determining the interpolating polynomial, because that would be a straight line. So we join these discrete points with individual straight lines. And once we have done that, then you can very easily calculate the area under those interpolating straight lines. Sum them up, you have got an estimate of what the total area is. And that is what the solution, or you can say evaluation of that integral, definite integral means. So I hope this point is clear to you. Just as a summary, we have two different kinds of categories of numerical integration. One for known functions, one for tabulated functions. And both these different categories can be dealt with these two rules or methods, trapezoidal method and the Simpson's method. First of all, let us look at the trapezoidal. This is obviously a technique for approximating definite integrals, and it works by approximating the region under the graph of the function fx as a trapezoid and calculating its area. So here is again the same curve fx. We have the lower limit of a and the upper limit of b, and we are trying to calculate the area of this trapezoid. So how do I create this trapezoid? We just join the 2 points on the curve which are intersections with the lower and the upper limits. So join this point with this point, and that creates a trapezoid, as you can see. We are also familiar with the formula for area of a trapezoid. So this is half of the sum of the lengths of the parallel sides. That means this one here and this one here. And that should be multiplied by the perpendicular distance between the parallel sides. So that would be the area. This is FA and FB. Those are the functional values. So what would be the sum of the length of parallel sides? That would be simply FA plus FB. And what is the perpendicular distance between the two? That is B minus A. So quite simply, we have an expression of I equal to half into FA plus FB multiplied by B minus A. That approximates the area under the curve. But is that a good approximation? If you go back to that slide, you can see that quite clearly this entire portion has been left out. This curved portion has been left out of it. So that basically constitutes an error. This is not a good approximation. So we have to find out some way of improving this estimate. What can be done? We can, of course, subdivide this entire interval into two sub-intervals. We have taken the midpoint, let's say represented by x1, and now we have two intervals of equal spacing. The equal spacing is represented by h, and h is given by b minus a divided by 2. This is just simply dividing the interval into two halves. Now we can join the appropriate points and get two individual trapezoids. Area under these, or area of these trapeziums can be joined up, summed up to find out the total area. So now you have I1 plus I2, where this area, this is I1 and this is so we can write the expression like this, sum it up, and we get an approximate estimate of the definite integral like this. So this is h by 2 fa plus fb plus twice of f of x1. Now it is visibly clear that the error here, that means the part which is unaccounted for, which has not been taken into this calculation, is this much. And that is as compared to the previous one, quite less. So basically, by subdividing the interval, we are getting rid of the error, reducing the error. So we can take this forward. I can now subdivide the entire interval from A to B into n number of subintervals, and that would reduce the error by a greater extent. So what is the general idea? Split the interval AB into a sequence of n smaller subintervals of equal width, which is given by H, and then apply the simple trapezoidal rule to each of the subintervals. I'll divide it like this into n number of intervals, each of them having a width of H, which is equal to B minus A divided by n being the number of intervals. And then I can create these trapezoids by joining the appropriate points. The area of these trapeziums would then be summed up as I equal to I1 plus I2 going up to In. So we start with I1, this is I2, like that it will go up to I. All of them can be summed up, and that gives us an expression like this. So the first one, I know that this is half of H, that is the perpendicular distance between the two, multiplied by Fa, this value, plus f of x1. You can see it here. That's what we have written as the first one. Next, I2 is again half of H, that is the distance, perpendicular distance, multiplied by f of x1 plus f of x2. Like that, we'll sum up all the trapezoids that are present. Once we do that, then we can simplify it like this. Here, just notice that these points or these values actually appear twice, right? Twice, because it is part of the end of the first trapezoid and the start of the second trapezoid. So it has been taken twice, and you can see that it appears here as twice of F1. Similarly, twice of F2 going up to twice of Fn minus 1. What about the first and the last? This one and this one, they appear only once, because there is no, let's say, overlap with another trapezoid. And that is why they are taken as Fa plus Fa. So note this, that is present. So we can further shorten this expression by using a summation here, and that summation would be going from 1 to n minus 1. So the expression is half of H, Fa plus Fb plus twice of this summation over Fi, where I varies from 1 to n minus 1. So how many total points are present? Let's say if this is denoted as the 0th point, this will be the n plus 1th point. This is 1, this is 2, 3, like that it will continue. This is nth point, and this one is n plus 1. So total n plus 1 points are there. This is F0, you can say. That one is the 0th point, and this one is the n plus 1th point. The others, starting from 1 going up to n minus 1, would be taken care of by this summation. Okay, by the way, this is not n plus 1. I think I made a mistake here. This is n. This is n minus 1. Start with 0 going up to n. That is in total n plus 1 number of points. So this is going to be n. So I think this the concept of trapezoidal rule is pretty clear to you. Uh, Next, let us look at how can we apply the trapezoidal rule in case of a tabulated function. Remember that we have two different types of integrations. One for the continuous expression, given expression, known expression. The other one for tabulated functions. Here, uh, it is based on fitting a polynomial through a specified set of points. These are the set of points that actually define the function. These are discrete points given in a tabular form. So there are xi's and yi's or fi's. Once we have got the interpolating polynomial, then we can obtain the estimate to the definite integral by using the same principles as discussed before. So here we have the tabulated function. You can see corresponding values for x's and the y's or f's. So x0, f0, x1, f1 going up to xn, fn. So total n plus 1 points are present here. Now, here we consider that these xi's are equally spaced with a gap of h between the points. So we can write it like this. So x1 would be x0 plus h, x2 would be x0 plus twice h. Like that, we'll go up to xn, which is given by x0 plus n into h. N plus 1 number of points gives us n number of intervals. So that is the graphical representation of the points that are shown in this table. And if we drop perpendiculars from each of them, we'll get these lines like this. So we start from x0, for which the functional value is f of x0. We go up to xn, for which the functional value is f of xn. Now, the simplest technique here is to fit straight lines through the points and determine the area under the straight line. That is the approximating function. So, those are the straight lines that we use. You can see that now we have automatically obtained the different trapezoids. N number of trapezoids have already been formed. So, these are the n trapezoids. And how do we get the area, total area? We simply sum them up like we did before. And what we'll get is the same expression at the end of it. So although one technique is for a known function given as fx, and the other one is for a tabulated function given as xi's and fi's, at the end of it, the final formula that we obtain is the same for both. And you can see it right over here. That is the function. This one.
Sir, if, to implement the trapezoidal rule, we have similar length of interval, but what if the length of the interval changes, sir?
If it changes, it is also possible to apply the trapezoidal rule for differing intervals, but then you cannot use this formula directly. What you will have to do is you will have to go back to this step. Here you will have half of h1 f of x0 plus f of x1 plus half of h2, which is the second interval, then fx1 plus fx2. Like that, individually, each of these different uh, trapezoids and their area would have to be taken care of. But it can definitely be done. Is that clear?
Yes, sir.
So individually, h1,
Yes, sir.
h2, h3, these need to be calculated. That means what are the distances between these different points? That can be easily calculated because you have the tabulated values here. So x1 minus x0 would give you h1, x2 minus x1 would give you h2. Like that, you can calculate all the different intervals. And once all the different intervals are available to you, you can simply go ahead and use them in the general expression. General expression for the area of a trapezoid. Okay.
Yes, sir.
So next we move on to the algorithm, how we can implement this. So basically, we'll just simply modify the expression like this. We'll take the half inside. The half has been taken inside here. You can see that. And that half multiplied by this 2 gets rid of the multiplier over here. So our algorithm, as it always starts, is with taking the input. What are the inputs that you need to take? You can take the number of subintervals, n, h is the interval length or width, and x1, which is the first point on the interval. Now this input can be taken in different ways also, depending on what type of integration you are performing, whether it's for a given function or is it for tabulated values. So depending on that, this part of the algorithm is likely to change. This one is for a given function. So for that, if you have the starting point, that means the lower limit, the width of the intervals, and the number of intervals, you can get the end of the interval also. That means the upper limit can be calculated. So here we start with a for loop which varies from 2 to n plus 1 with steps of 1. If you write this expression xi equal to x1 plus I into h, that will give you the x values at which the functional value would be required. So those are basically the subinterval definitions. Starting with x1 going up to xn plus 1. By the way, just notice one thing, that in the expression itself, we had used the notation f0 that corresponds to x0. Here, note that we have started from x1. So there is basically one small shift. It does not exactly correspond to the formula provided at the bottom of the slide, because there in these expressions we have used x0 and f0 as the first point. In the algorithm here, I have used x1 as the first point. That's just you can say a small oversight on my part, but you can still use x0 also for this. But for that, the for loop will start from 1 for I equal to 1, go up to n. So always remember that total n plus 1 points should be present. If you start from 1, then you are going up to n plus 1. If you start with 0, you will go up to n. Just keep that. Now the next step is another for loop. Here we will calculate the functional value at the points or the xi's that we calculated in the previous for loop. So this will vary from 1 to n plus 1 with steps of 1, and you can read the functional values fi's, or you can calculate them from the given function. As I said, this input part, it is likely to change depending on what kind of integration you are doing, whether for a known function or for a tabulated function. So be careful with that. Next, we take a variable sum, and within that, we store this summation f1 plus fn plus 1 divided by 2. Why we have done this? Take a look at this part. Except the h part, h is not there. So this is half of f0 plus f1. That is what we have calculated in this expression, allowing for the change in the notation. That is, here we are starting from 1 going up to n plus 1. Here we had started from 0 gone up to n. So with that mentioned, we are calculating f1 plus fn plus 1 divided by 2 and storing it in the variable sum. Now we take a for loop to carry out the summation. The summations we have already discussed in our previous classes, probably in regression, how to do this summation. So sum would be equal to sum plus fi. All the fi's are already known. So for each iteration of this for loop, one of the functional values will be added to the previous one and stored in the sum variable. Once the for loop is over, you will obtain this summation fi with I varying from 2 to n. This summation will be calculated. So what is left? Do note that already inside sum we had f1 plus fn plus 1 divided by 2. So once this for loop is completely over, you have the summation within this parenthesis, third bracket. So what is left? Simply multiply it with the interval width h and get the final value of the integral. Once you have got that, write it out, display it, and stop the program. So it's a very simple implementation of the trapezoidal rule, composite trapezoidal rule, which can be converted to a C program without too much difficulty. Any questions up to now?
No, sir.
Okay. So moving forward, this is just a visual explanation. It's a demonstration of how, by increasing the number of subintervals, we can, in fact, reduce the error. With one subinterval or one interval, you will have maximum error. As you go on increasing the number of intervals, the error would reduce, and probably you will require some termination criteria at the end of it to see where you can stop the number of intervals. Here, there is an important point to note is, if you are doing an integration for a known function fx, then you have to decide upon what should be the value of n, number of subintervals. You cannot go for a small number, that will increase the error, and if you go for a very large n, that will increase the computational burden on the computer, and it will not improve your results by too much. So choice of n is a very important thing. How can we do it? Let's say that for this function fx, simple function like this. This is x0, this is xn, and we have got two intervals like this. So we can start with n equal to 1. In the next step, we can go to n equal to 2. For each of them, we are calculating I. Let's say this is I1, this is I2. Now in the next step, I'll subdivide it again. Both of these intervals, I'll halve it. So now I have 1, 2, 3, 4. So n becomes equal to 4. For that, I'll calculate I4. And you will see that as you proceed like this, your estimates will improve. Error will decrease. Next, I'll again halve it. N becomes equal to 8. So this is I8. If I continue, it becomes 16. This is I16. But why do we stop? I can make it 32, I can go to 64, 128. But there should be some criteria that makes you stop this halving of the intervals. Basically, what we can do is compare I1 to I2, then I2 to I4. At the end of these iterations, we'll compare the present estimate to the previous estimate. So I present minus I old. If you want relative, you'll divide it with I present. So that is sort of, you can say, an error estimate. If this error estimate falls below epsilon t, then you can stop. Let's say after coming to n equal to 8, this one is satisfied. So we will stop it here. This only works for a given function. Obviously, if you are going for a tabulated function, then you do not have the luxury of calculating the functional values for newer and newer points. In that case, you will be given a fixed number of xi's and fixed number of functional values fi's. On the basis of that, you will have to calculate the estimate of the definite integral. So there you do not have any choice of halving the intervals and increasing the efficiency or accuracy of the results. There you work with what you got. But for this sort of functional representations where the exact expression is known, this sort of a scheme can be set up to optimize your calculations and computations. So this is just again another simulation of how to calculate the formula. We have already discussed this, so I'm not going to go into it in detail. But you can see that with delta x, which is representative of h here, with higher h, you have higher error. Sorry, if the number of intervals are less, that is higher h is there, you have higher error. If you increase the number of intervals, h reduces. Along with that, the error also reduces. In fact, you can reduce the error in this trapezoidal rule as of the order of h cube. So this is the magnitude of the error is of the order of h cube. So if you half the interval. That means previously it was h, now you make it h by 2. In that case, you are reducing the error by 8 times. So error becomes 1/8 if you half the interval. So that is all regarding the trapezoidal rule. Next, we'll go for the Simpson's rule. In Simpson's rule, uh, we approximate the region under the curve fx by considering a quadratic form, a second order polynomial. And as it is a second order polynomial, it has to be fitted through 3 points. Previously, it was a straight line, so it required 2 points. Now, as we are using a quadratic curve, we will be needing 3 points like this. So f of x0 at x1, which is x0 plus h, you have f of x1, and x2, which is equal to x0 plus twice h, you have f of x2. So these are the functional values and the x values. So here what do we do? We fit this second order polynomial represented by f2x. The interval is again h, as already shown. Now the form of this second order polynomial is a0 plus a1x plus a2x squared. For ease of computation, what we'll do is we'll shift the origin. The origin is here at the moment. You can see it's right here. So we'll shift it to the middle point, to here. The middle point is x1, so we'll shift it there. So x1 becomes equal to 0, that is the new origin. What about x0? It is at a distance of h in the negative direction, so x0 becomes minus h, and this one at a distance of plus h from the origin, so it becomes h. So minus h, 0 and plus h are the 3 points after the shifting of the origin. The functional values, of course, are fx0, fx1 and fx2. In short, they are written as f0, f1 and f2. Now, our task is, of course, to find out these 3 unknown coefficients, a0, a1 and a2. These are the 3 unknowns. We need 3 equations for this. For solving these 3 unknowns, the 3 equations can be obtained by putting the values of the 3 points. If we do that, we'll have f0 equal to a0 minus a1h plus a2h squared. Quite simple really, we are putting minus h in this expression. So a0 minus a1h plus a2 minus h square will be plus h square, so that makes it a2h square. What's the functional value over there? That is f of x0, which means it is f0. The next point, the variable is 0. So this is 0, this is also 0. So you have f1 equal to a0. So quite simply, it means we have already solved one of the variables. a0 is now known, its value is equal to f1. What about f2? That is the third point. So we'll put h in place of x, and that makes it quite straightforward. a0 plus a1h plus a2h square, that would be equal to f2. As I said, we already have got the value of a0. So what about a1 and a2? We can solve them quite easily. First of all, I will subtract the first from the third equation. And then we can manipulate it to obtain the value of one of the unknown coefficients. We can also add these two up and get the value of the third unknown coefficients. If we add them up, then you can quite easily see that this minus a1h and plus a1h gets cancelled. We are left with this twice a2h square. So here if I do that, let's write it out. A0 minus a1h plus a2h square, and f2 is again a0 plus a1h plus a2h square. So if we add them up, this gets cancelled. This is f0 plus f2 equal to twice f1, because a0 is equal to f1, so that would be twice f1 plus twice a2 h square. From there we can write twice a2 h square as equal to f0 plus f2. Twice f1 can be taken on the left hand side, that makes it minus twice f1. Similarly, if we subtract the third equation from the first, you will get the value of a2. So now we have solved a0, a1 and a2 in this form. Obviously a2 can be written by dividing throughout by twice h square. But we are not going to do that because it will help us in the next step. So how do we get the area under the second order polynomial? That is f2x. We can carry out this integration. Notice that here the limits of the definite integral has changed. It was previously from a to b. Now after the shifting of the origin and the change of variable, it's becoming minus h to plus h. So a0 plus a1x plus a2x square to be integrated over the domain minus h to plus h. It's a simple integration. You can carry it out and you will get this. So a0 integrated with respect to x gives us a0x plus a1. There is an x over here, so it will become x square by 2, and this becomes x cubed by 3. And the domain is minus h to h. Put them here. Obviously, because
ভয়েসটা গ্লিচ করলো।
okay, which part should I repeat?
স্যার ওই জাস্ট ইন্টিগ্রেশনের ওখানে কি বলছিলেন কি কেটে গেল ভাবে।
Okay, this integration is quite simple. Means even if I do not explain, I think you can carry out this integration. This a0 integrated with respect to dx, what it will give? A0x plus, then the next term, this will be x square by 2, so a1 x square by 2. X square integrated gives us x cube by 3. So that is the integration with these two limits minus h and plus h. Next we'll put them here, and you can see that because this is a square term, it will become a1 h square by 2 minus a1 h square by 2. So this will go to 0. What you will be left with is only the first term twice a0 twice a2 h cube. Take h common, we have twice a0 plus 1/3 twice a2 h cube. Simple mathematics. Now you see why we had kept twice a2 h square here. We can directly replace that from here. We'll take it, put it here. So we have this expression. Simplify this and you will end up with the final expression of the area as h by 3 f0 plus 4f1 plus f2. So that is the total area. Obviously it's an approximate estimate. Now We can go for the composite of this rule as well. So we'll consider the composite Simpson's one third. Now, why is this called one third rule? That is because of this coefficient here. That is 1 by 3 is present at this location. So that is why this is called Simpson's one third. If I had taken a cubic polynomial here, then this coefficient, this multiplier would have been 3 by 8. That's why the other Simpson's rule is known as Simpson's 3/8. However, that is not under discussion at the moment. What we'll discuss is composite Simpson's one third. This is just a demonstration of how we can take 3 points, create quadratic polynomials for them, and we can also reduce the h, that is width of the interval, take more number of subintervals, and improve our estimation. Again, just a simple simulation to clarify the point. For the expressions that we will be using, we need what we discussed in the previous slide. But one thing to be noted here is that n, the number of subintervals, need to be even. If it is not even, then you cannot apply the Simpson's one third, because we are taking 3 points at a time. So total number of points need to be odd. Total number of points is of course n plus 1. N plus 1 has to be odd so that n becomes even.
কেন স্যার চারটা পয়েন্ট দিয়েও তো স্যার কার্ভটা ফিট করা যাবে?
If you take 4 points, then how would you fit a quadratic polynomial? You will have to take 3 points. So first 3 points you will take first. That will create the first polynomial. What about the second one? Now you are left with only 2 points, isn't it?
Yes, sir.
So that will create a problem. In those situations, what you can do, suppose you have even number of points. You cannot apply Simpson's rule directly. What you can do is, for the first interval, take 2 points, apply trapezoidal rule. If you take those first 2 points and take them out, then you are obviously left with odd number of points after that. So let's now see what is the composite Simpson's rule. And just like in the composite trapezoidal rule, you can subdivide the interval into n segments and apply Simpson's one third rule repeatedly over every 2 segments. Remember that here it has to take into account 2 segments consecutively, because we are taking into account 3 points. Again, I would remind you that n needs to be even. If n is not even, then you cannot apply the Simpson's one third. Let's look at these points, discrete points present here. So these are the functional values at these points. We start with f0, end at fn, and these are the sort of polynomials that you can fit. Now here you see that if we had taken 4 points, that means you start with f0, end at f3. That's 4 points. 1, 2, 3, 4. So for the first 3, no problems. Take f0, f1, f2, we can fit this polynomial. But what about the second one? Now you cannot fit a quadratic polynomial through these 2 points, 3 and 4. So that creates a problem. That is why this n needs to be even. So if you are talking about 4 points, then what I would suggest is consider trapezoidal rule for the first two. That means the first interval should be calculated through trapezoidal rule. The next 3 points would be used to fit a quadratic curve like this, something like this. Then you can apply the Simpson's one-third rule for the next 2 segments. Anyway, uh, what would be the composite area? How many segments are there? Number of segments would be n by 2. Total number of segments is of course n, but number of what should I say? Number of polynomials, number of integrating polynomials would be n by 2, and that is why we have added from I1 to in by 2. The individual areas for these polynomials are known. That comes directly from what we have discussed in the previous slides. That is the expression h by 3 whole multiplied by f0 plus 4f1 plus f2. That is for the first 2 intervals for this interval. That is I1. You have f0 here. The middle one would have a multiplier of 4. You can see 4f1, and then there is f2. The next one would be starting with f2, ending with f4. The middle one is f3, and you can see that there is a multiplier of 4 over here. Similarly, we'll go to the end of the points, that is the nth point, and that would end with h by 3 multiplied by fn minus 2 plus 4fn minus 1 plus fn. Sum it all together, and then you will have the expression like this. So h by 3 f0 plus fn, that takes care of this term and this term. All these terms having 4 as multipliers are taken over here. Notice that here only the odd numbered functional values make appearance. You have f1, you have f3, you will have f5 going up to fn minus 1. It is important to note this from the point of view of your programs. It will help you while writing the algorithms. But that is not all. You have these even terms as well. And you can see that there is a multiplier of 2 before them. Why does it happen? That is because you have f2 here, also have f2 here. That is the end of the first subinterval, start of the second subinterval. That means this one. It is part of this curve, end of this polynomial. It is also part of the second polynomial over here, starting of the second polynomial. That is why it appears twice. And it will happen for all of the even points. That means f2, f4, f6 like that, going up to fn minus 2. That is what is written over here. You can see summation I goes from 2 to n minus 2 only for I even. So it will jump from 2 to 4, 4 to 6, like that it will go up to n minus 2. Similarly here, when I goes from 1 to n minus 1, I is odd over here. So it will go from I equal to 1 to 3 to 5 to 7 up to n minus 1. So that is the entire expression. And with the help of this, you will have to estimate the definite integrals for composite Simpson's method. How do you write the algorithm for this? In fact, the input part and the preliminaries are the same as the uh, trapezoidal. But inside the loop where you are performing the summation, you will now need to take care of two different summations. One corresponding to the odd indexes, the other corresponding to even indexes. So probably you can install a if-else statement, condition checking, check whether I is odd or even, and according to which condition is satisfied, add that particular functional value to the appropriate summation term. Once the summation is completed, then you can add it to the first and the last functional value multiplied by h by 3 and get the final answer to the definite integral. Any questions from here?
No, sir.
Understood?
Yes, sir.
Yes, sir.
Okay. So that is all for today's class. Thank you.
থ্যাংক ইউ স্যার।
Okay.
স্যার
So,
ভুল
হ্যাঁ বলো।
মানে স্যার এটা এর আর কি কি বলবো মানে পড়ার ব্যাপারে ঠিক নয়, মানে বলছি স্যার এই আপনি এই স্লাইড গুলো তৈরি করেন, এই যে ফাংশনের যে স্লাইড গুলো, এগুলো স্যার কি করে তৈরি করেন? মানে
কোনটা
পাওয়ার
বলো?
পয়েন্ট যেমন ওই ট্রাপিজয়েডাল এটা দেখানোর সময় আপনি যে ইরর গুলো কিভাবে কমছে, ওটা যে মানে প্রেজেন্টেশনটা করলেন, ওটা কিভাবে তৈরি করেন? মানে ওটা কি পাওয়ার পয়েন্টের ভাবে তৈরি করা যায়?
হ্যাঁ, পাওয়ার পয়েন্টে তৈরি করতে পারবে, but obviously you will have to give some time. I'll show you.